ramifications. The primary ramifications of this are either that magma ocean crystallized significantly later than most of our estimates, and many of these ages here are incorrect, or alternatively that the chrononorthosites simply aren't the flotation cumulus that we expect them to be. Okay, so by way of approach, we did three things that were somewhat unusual for isotope geochemists. First of all, we actually looked at the rocks. We spent a couple of days in the curation facility culling through samples of 60025. We found a class in here that was dominated by pyroxene. This was in fact enabling, although the rock, of course, is a little bit atypical of classic chrononorthosites, which have much smaller abundances of pyroxene. The other thing we did was we developed a washing procedure for the uranium lead chemistry, or lead chronology, that was specific to this sample. In other words, we took fractions of the sample, we developed a washing and analytical procedure, and then applied it to give us the most precise lead chronometry that we could. And finally, we produced a 4-9 pure neodymium-150 spike. And this allows us to determine samarium-neodymium ratios and neodymium isotopic compositions, in particular 142 neodymium isotopic compositions on the same fractions. We did this because our experiences is showing us that when we take an aliquot for spiking to determine samarium-neodymium ratios, we often seem to see discrepancies that may indicate that things are fractionating in the liquid. So the samarium-neodymium ratio that we determine on one fraction of the sample is not appropriate for that, for the isotopic composition that we determine on the other portion of the fraction. So we began by doing the classic mineral separation procedure, which is outlined here. In a nutshell, what we did was we did a very gentle crushing of the sample. We removed the plagioclase and the pyroxene using tweezers, and then we put those two fractions plus the remaining bulk rock fraction that we had from that picking through a Franz separator, and generated 6 pyroxene, 6 plagioclase fractions that were then combined. The total separated fractions that we had was about 600 milligrams of whole rock and about 500 each of pyroxene and plagioclase. The 10 milligrams of the pyroxene and plagioclase were then used to develop the washing procedure for the lead-lead analysis. Once that was developed, and I should say we presented this last year at LPSC, but what we did for the washing procedure was we sequentially washed these fractions and measured the isotopic compositions of the washes. So we did something like 23 different washes and 23 different measurements, and then we started digesting the samples to get the material that was least contaminated to use for the chronology. Then we took 100 milligrams of pyroxene fraction for the final lead-lead chronology. We didn't do the same for the plagioclase because we found that it was completely contaminated and we couldn't easily distinguish the radiogenic component from the contamination component. And then finally, the remaining fractions were used for the samarium-neodymium chronology with our spike. So the lead-lead chronometers presented here. I'm not going to spend a lot of time on this because we presented this last year, but the various pyroxene fractions that were analyzed here lie on this line here. Of course, on this type of diagram, you have 204, 206 lead, and it's 207, 206 lead. It's the intercept here that defines the age. You can see we were able to find fractions that essentially intercepted the y-axis, and this is what resulted in giving us very small uncertainties. The age we determined for this fraction was 4.359 billion years, with an uncertainty of about 3 billion years. And again, the plagioclase was not used because we found that it was dominated by contamination. We also completed samarium-neodymium chronometry. This is one of the 2 chronometers that are used, samarium-147 in the case of neodymium-143. Of course, there's the parent isotope here against the daughter here. The 3 fractions that we analyzed were pyroxene, plagioclase, and whole rock. A line regressed through these has a slope which is proportional to the age. In this particular case, we have an age of 4.367 plus or minus 11 million years. So this age is in good agreement with the lead-lead age and gives us good confidence that we're actually dating the age of the rock. The other point to note here is that the initial epsilon neodymium value, which is an indication of the long-term elemental composition of the source regions from which these are derived, is consistent with what we would expect based on the composition of the source region derived from trace elements. As a result, this isochron, from all extensive purposes, looks like the crystallization age of the rock. One of the things that became immediately apparent, however, is that this age is about 73 million years younger than the previous age that was determined by Carlson and Lugmeyer. And Lindy, you made note of this in your talk today, that there's 2 ages for this sample. We postulate that our age, or we will argue that our age, I think, is better because we're dealing with much larger mineral fractions and we're less likely to be susceptible to corrections associated with blank. In addition, the mass spectrometry was using large fractions, so we can analyze the neodymium as a metal beam, which gives us more precise information, more precise ages. But ultimately, the nature of this uncertainty is a little bit mystifying, and the nature of the difference is not well understood by us. The second chronometer that we applied is samarium-146, which decays to neodymium-142. Now this is, of course, an extinct chronometer. Samarium-146 has a half-life of about 100 million years. The various fractions that we analyzed are represented by these lines here, and a line regressed through this data set yields an age of 4.312, plus or minus roughly 30 to 35 million years. Note that previous whole rock analyses that have been done by Maud Boyette here, published in 2009, lie right in with the whole rock data. So our data are completely consistent with what the DTM group has done in the past. One problem, however, of course, is that this age is slightly younger than what we would expect. It's discordant from the lead-lead and samarium-neodymium